Hello everyone, I'm Im Jonghyun, the presenter of Team 2. The members of our team can be found below the page. This is our weekly plan. This week, we are going to study on Bing Roof Cantilever. I'll proceed with the contents as below. Before main presentation, I will review the last week. Last week, our team presented about double cone. The double cone acts as a support for the load of a Bing roof and carries the load well to the lower support surface. It plays the biggest role in this structure and allows the existence of the world's longest cantilever roof. And now, I'll present about the Bing roof. For the design of the Bing roof, which has the shape of an 85-meter long span, a structural system was needed to reliably realize the design of the roof. The next slide will explain the 4 ways to effectively support this roof structure. 4 structural systems are applied to provide stable support for roofs with long span. When the loads are subjected, convert moment load of crown truss beam to vertical load. Double cone that supports the roof and shear wall to transfer vertical load to mat foundation. So now I will explain about truss beam. The point of truss beam is that the truss of diagonal members exist vertically in a 5 meter multiply 5 meter unit. And the biggest feature of this truss unit is that the size of the member is set differently. Here, both the upper and lower sections of the truss have rectangular sections. The size of truss members varies from 200 mm multiply 200 mm to 700 mm multiply 400 mm, creating an economical effect by placing large cross-section resistant members on the heavily loaded side and a relatively thin section on the relatively low load side. In addition to this vertical unit truss unit, horizontal trusses were also placed to prevent horizontal behavior. For horizontal diaphragm action, the lower and upper surface are tied together by means of tension load and 20-meter centuries. For the roof, the truss unit had the same back, but the part that should be used as the dining area did not have diagonal truss members in the usability gate of the space. Instead of trusses, this part uses a moment frame system consisting of vertical horizontal steel members to form the structure of the roof. So, how is the roof supported for earthquake-like loads? Of course, the building itself is designed to effectively respond to earthquakes of magnitude 6.6, but there are additional installations of the roof. This roof structure has a system that is uniquely connected to the cinema mountain through a horizontal pin and is horizontally supported by the cinema mountain, when an earthquake occurs. It also had to be considered at the time of design that the cantilever structure would be deflected by its own weight. In general, long-span cantilever structure is more prone to sagging by the weight of the building over time than other structures, and the Busan Cinema Center was no exception. Therefore, the structure of the cantilever in Busan Cinema Center was produced through a 45 cm truss uplift design, and the exact value of the truss uplift was predicted and entered and applied was a very challenging part. Therefore, as a solution to this, the Busan Cinema Center introduced the Tekla system. Tekla Structures is a building information modeling tool that used CAD standards to create fully interactive structures for all construction projects. Save time, applying complex loading. Tekla Structure Designer automatically calculates and applies gravity and lateral loads to the model. We were able to improve the accuracy with minimized errors by inputting accurate data to each member through Tekla 3D modeling. The values of center of gravity from Tekla improved the efficiency of operation of tower crane in the construction site. Next, I will show you the wind tunnel test. As the wind hits the building, it creates a vortex. And when the building and wind vibrate together, the building shakes greatly. This is same that if you roll your foot against the swing's vibration when you swing the swing going further away. The structural analysis of the roof has been performed using the FE software LSTAP and reviewed by Midas Gen. The roof has been idealized by means of a full 3D model. Wind tunnel test was conducted in March 2008 before construction began. The FE model allows the interpretation of eigenfrequency values to predict instability such as spikes or wavering. As a result of the wind tunnel test, if a typhoon occurs, the roof of the cantilever in the front may shake about 85 centimeters. This is very small at 1% of the total span. To prevent this, the end support system was used for the front part of the roof. There is an unusual part of the system that supports this big roof. It is a dynamic end support system. This end support system comes from the ground located on the front of the big roof. When an emergency situation, such as a typhoon occurs, which effectively supports the rocker load on the roof, wind loads act. In the case of this end support system, the 10-stage steel pipe boom settled in the underground parking lot pitch rises in the event of an emergency attached to the beam roof truss. And the lower part of the roof and the upper part of the boom stand are each equipped with a damper holder to effectively support the load. The existing structure is designed to withstand strong winds of 40 meters per sec and 60 meters per sec. Maximum instantaneous wind speed of 60 meters per sec, but it is designed to effectively withstand the cantilever roof, even with a maximum instantaneous wind speed of 70 meters per sec. Supporting the end of the roof to prepare for weather changes such as a super typhoon in case of emergency. Another thing used to support the roof is back tie. This back tie structure has a total of 2 and is connected to the rear roof to support the roof through tensile force and is applied to adjust the balance of deflection and other earthquakes due to wind load. That load act. Our presentation is over. Next week, we are going to study about lift-up method. Thank you for listening. We were Team 2.